started, let me make a brief recap. And I apologize for taking 2 minutes to make a recap. I think it is important. And let me go then at the beginning of what we discussed about wave forces. And the recap is as follows. First of all, we have to get an interpretation of the complex dynamic that is originated by waves acting over a ship. And the complex dynamics is based on some premises. The first premise is that the ship is a rigid body with 6 degrees of freedom. And these 6 degrees of freedom can be seen in the figure here are movement of the ship, translational movement along the 3 axes, Z, Y, and X, and rotation around these 3 axes. The 3 axes are called X here is the longitudinal axis, Y is the transversal axis, Z is the vertical axis. Now, this rigid body, once is impacted by waves, can undergo then rotation and or translation, rotation around the axis and translation along the axis. Now, we can identify 3 axes, these 3 axes in any ship, and let's focus on the technical terms that we use to denote these 3 rotation and 3 translations. So about rotation, there is roll, which is the rotation around the longitudinal axis. There is yaw, it's rotation around the vertical axis, and pitch, it's rotation around the transversal axis. The most important ones are roll and yaw. Pitch is originating a little oscillation, a little rotation of the ship. And then let's talk about the translations. They are called, and by the way, I realized that I forgot to discuss these 3 movements, the technical term of translations. So let's focus on the screen. Translations are called sway. It's the translation along the transversal axis. There is surge. Surge is a translation around, along the longitudinal axis. And then there is heave. Heave is translation around the vertical axis. Let's also note, I use the term translation, which is the correct term. It is the same term that we use to mean translation between languages. But the correct technical term is translation. To avoid misunderstanding, sometimes I say movement along the axis because translation may be something that it's a bit confusing, but actually it's the correct technical term. Okay, now what I said is that this is a complex interaction between waves and ships with the possible resonance, and we have resonance when the period of waves is comparable with the period of oscillation of the ship, and this complex interaction, dynamical interaction, is impacted by many behaviors variables, including those ones that you see in this list of bullet points. Characteristic of waves, configuration of berths, elastic characteristics of the fenders and mooring lines, ship characteristics, and type of ship movements. And then let's say another premise. Wind forces on moored ships are originated by 2 distinguished but interacting processes. The first is the up and down movement of waves. So it's an oscillation. And the second type of wave force is called the drift. And the drift is a net force in the direction of wave propagation. What causes the drift? The drift is caused by absorption or reflection of waves by the ship. So waves carry momentum, they carry energy, okay? Momentum, you can assume that momentum is directly connected to energy. Momentum is a vector because it has the direction of the wave. And when structures like ships modify the behaviors of the wavefront and then modify the momentum of the waves, then a reaction is originated. And the drift force is a steady force in regular waves and a slow varying low frequency force in irregular waves. Now, you know, this we have to be careful about these low frequency varying forces in irregular waves, because their period it's often comparable with the range of the natural periods of moored ships. And this range is in the range 20 to 100 seconds. So take this as an order of magnitude. An order of magnitude of the period of moored ships. So basically, keep in mind these two types of forcing originated by oscillation, the first one, and the second one called the drift, which is originated by the momentum that is carried by waves, which is modified, it is impacted by the presence of the moored ship. And, you know, to better understand the complexity of the problem, and in particular, to better understand the general behavior of the stresses that are originated by waves, there is the Port Designer Handbook provides the following guidelines, which I am now projecting on the screen. And let me explain why we need guidelines. So we already said that the problem is complicated. You know, it's complicated. It's more complicated with respect to wind, because wind, in general, it's a force that is acting along a direction with, and it's a steady forcing. So it's different with respect to waves, which originate an oscillating forcing and a drift, which are interacting each other depending on the behavior of the ship. And the most important one that we have to consider is the oscillation period. And also depend the interaction between waves and ships on the direction of the wave and the behavior of the ship and the berthing structure. And this behavior, why are so important with waves and less important with wind? Because waves originate an irregular forcing. So the elastic reaction of the mooring lines and the elastic reaction of the berths play a more relevant role. With wind, we have a constant forcing. So you have a constant resulting force against the ship, and therefore elasticity is less important. And so in order to understand, I anticipate one of the conclusions, in order to understand the interaction in the details between waves and a moored ship, what we need is a small scale physical model. For very complex situations, what we do is to make experiments in the lab, because you can understand that sometimes you have different type of waves interacting, and the interaction may be nonlinear. So the linear theory can have a limited applicability in this case. And therefore, for complex situations, for important designs, what we do is to make experiments in the lab. So we build a small scale pool, and then we transfer the results that we get in the small scale pool to the situation of the port. Keep in mind that this looks like a simple exercise. In reality, it's not simple. First, because you need an infrastructure, you need a huge lab. And second, because The results from a small-scale hydraulic model cannot be merely transferred, cannot be just assumed as equivalent to the real situation, to the prototype. We call the real situation the prototype. So the results that you get in the small-scale model cannot be simply transferred to the prototype. You have to account for the scaling effect, which, for instance, may bring some viscosity to come into play in the lab, because you compress the harbor into a small pool, so the viscosity of seawater becomes more important, and then you have to take into account this. And so it is an exciting exercise, just for the very reason that it's not simple. And in general, you need very large facilities. You cannot simulate a pool into a sink. Sorry, you cannot simulate an harbor into the small size of a sink. You have to simulate the harbor by involving a large pool. And I'm sorry that I cannot bring you to the pool that we have in the lab at the University of Bologna, where we make these kind of simulations. We study the effect of waves with a wave generator, and then we measure the action of waves against the structure of the pool, against the walls, and if we are interested in a ship, we place the ship into the pool. And I just want to mention to you, unfortunately, I don't have a video to show, but during the break, I may try to find some, I may try, during the break, I will look for a video. Actually, in the pool of our lab, we simulated the performances of a boat that was selected to participate at a competition. And the boat was, the competition was for, it was a speed competition. There was a tour that the competing boats were required to make with only solar energy. So basically zero emission boats. And so the boat was very light. And of course, the competitors, the producer, had to minimize the resistance of water to the movement of the boat, and therefore the shape of the boat was studied in the lab. And the boat was kept fixed. It was the water that was brought to move against the boat, and then they tried different shapes of the keel in order to minimize the friction between the boat and water. It was really exciting. Anyway, so this is I anticipate my conclusion. This is a difficult and complex interaction, which in order to fully describe with details, you need to reproduce in the lab. But of course, we, especially for small designs, often we don't have the opportunity to go into a lab and make an experiment. And therefore, we need to provide some simplified computational schemes for design. And this is the purpose of what we're discussing today, how to simplify this problem. And you will see that we can come easily to a simplification with the awareness that it implies some uncertainty. And in order to introduce the simplification, let me first discuss these guidelines. So, first, mooring line forces are induced almost entirely by waves of period longer than 20 seconds, with major contribution in the range 40 to 100 seconds. And this is important for you to understand what are the most dangerous situations. So, as I said, if you have a period that is very short for your waves, you are not very concerned, okay? Now, also keep in mind that usually, as you know, short periods are associated to short amplitude. In the largest amplitudes of waves, the largest wave heights are associated to longer periods. Now, rolling is triggered primarily by swells with period in the range 13, 19 seconds. Remember what is rolling. I go back, or let me change without going back, let me change the page. I have another page opened, and let me open the image. Rolling, okay? So it's generated by waves. So rolling is rotation around the longitudinal axis. It's generated by waves in the period 13, 19. Okay, let's go back to the previous page. Now, pitching is small. I already anticipated it. And insensitive, generally insensitive to the wave period, and pitching, small, okay? Let's talk about heave. And first, let me see what is pitching. It is this one, you remember, it's rotation around the transversal axis. And now let's focus on heave. Heave is up and down along the vertical axis. So what about heave? Let's see. Heave motions tend to equal the wave height at long periods and are smaller with short period waves. Again, these guidelines confirm what I already anticipated. And here you see what I said before. Analytical assessment is very complex, and therefore small-scale models tests are usually carried out. Now, let's look at now a simplified approach for design, okay? And again, let's refer to the Spanish standard. Why do I refer to this? I already explained to you. I prefer to refer to this standard because it's public domain. So if you want to get more details, you can go there and have a look, okay? But in general, keep in mind that, strictly speaking, these are guidelines that are suggested for the Spanish context. Once again, make sure that you get the correct guidelines, the correct guidance for the place where you are making your design. We are now referring to an international context. So it may be different context, may have very different guidelines. Now, this is very simple, and it gives you two empirical formulas with some physical basis to compute just a lateral force and a longitudinal force. So this is the result of the overall result of oscillation and drift, okay, which is expressed as a function of basically wave direction, height, and some ship behaviors. So the problem is reduced and it's tackled with a very simple approach. Two formulas for transversal forcing and longitudinal forcing, depending only on wave direction, wave height, and a characteristic dimension of the ship. So you understand that this is a simplified approach, okay? But it is very useful to get an order of magnitude and to make a preliminary design if needed. In some countries, in some regions, the law in force split the design procedures in two phases. There is a preliminary design and a final design. What is the purpose of the preliminary design? Usually to get the necessary authorization. Given that in some countries, when you apply for a permission to make an intervention, to build an infrastructure, you need a permission. And when you apply, in some countries, they may say no. So it's not worth spending a lot of money for a very detailed design, and therefore they require only a preliminary design for for the bureaucracy related to getting the permission. And therefore, in the preliminary design, you are allowed to use simplified methods. This doesn't apply to any country, but for instance, in Italy, it is, this is the approach that is usually practiced for very important infrastructures. And usually you have also to pass a competition where several alternatives for building an infrastructure are compared, and they base their comparison on the preliminary design. Now, let's look at this formula, which are given by a product of several factors, and let's focus on the first one, and let's see what are the variables that you see there. So first, you have a couple of coefficients, and the first is called CFW. It's called the water plane coefficient, and depends on the wavelengths at the location and the ship's drought D. Okay, remember what is the drought, which is, we discussed it here. Just 1 second. And sorry if I go back, but I think it is important to be very clear. So here the drought is D, okay? So it's the dimension, it's the distance between the water level and the bottom of the keel. Okay, now let's go back here. So basically, as I said, the water plane coefficient depends on the wavelength and the ship drought. And you can estimate it from an abacus, which I will show you in a moment, okay? Now, the second coefficient, CDW, is called the depth coefficient, which depends on the wavelength. And just 1 second, I need to shift this one. Okay, very good. Now, as I said, it depends on the wavelength and the water depth at location. Again, there is an abacus which I can show you later. And now I'm getting the abacus in the other window, so I can shift to it. Just 1 second. Here we are. Okay, so let me show the abacus to you. This is the abacus for estimating the water plane coefficient. And the water plane coefficient here, it's reported in the vertical axis. And in the horizontal axis, you have this product given by that is obtained by multiplying the ratio 2 pi divided by LW, where LW, as you may remember, it's the wavelength. And then there is the second factor, which is the drought D, okay? So you see that the water plane coefficient, basically, it's varying from 0 to 0.06. Okay, good. Now, let's go back to our formula. And then we said there is CW depth coefficient, which depends again on the wavelength and the water depth at location. And let me show you the abacus from which we can estimate it. So what you see, it's CW on the vertical axis, varying from 1 to 2. And on the horizontal axis, you have the ratio 4 pi times h, water depth at location, divided by LW, which is the wavelength. Very good. So these two abacus allow you to estimate these two coefficients. Now, the third factor is gamma W. Gamma W is the specific weight of water. For seawater, you can take a specific weight. It depends on the salinity, but you can take something like 1.025 for its tons per cubic meters, of course, and for higher salinity, it can reach a value of 1.035. So from 1.025 to 1.035, depends on the salinity. And so this is the specific weight of water. And these variables are described here with also their dimension in the list that follows, but let's focus on the formula for now. And then we have HS squared, and it's HS it's the design significant wave height, okay? And you know what significant means, and it's a reference value that is taken for the design wave. And then the next, and this is squared, so it has an importance because it's raised at the power of 2. And then the next one is d prime. It's the projection of the ship length in the direction of the wave. And how you can compute it? You can compute it by multiplying, and it is specified here, the length between perpendicular, you see here, d prime is computed, is given by the length between perpendicular times the sin of phi. We will see what phi is, okay? And plus the beam times cos phi, okay? Now, what is phi? It's the angle of the wave direction to the ship center line, okay? And here it says, see figure 6. Let's look at figure 6. 1 second, I get it. It's here. Now let me view it and bring it on your screen. So this is phi. So the red arrow gives the wave direction, and then phi is the angle between the wave direction, the acute angle between the wave direction and the ship center line, which is also called, we called also it ship longitudinal axis. Okay, keep in mind this angle, which allows us to define the direction of waves. Okay. So let's go up again. And we got to the end because we defined what is d prime, and then we multiply everything times the sin square of phi. This is the transverse force. Okay. Now, longitudinal force, there is a similar formula, and again there is the water plane coefficient, and there is the depth coefficient, and then the same formulation. Everything is the same, with the difference of the final factor, which is now cos square, not sin square. So cos square phi. It's very simple. So basically, you reduce the wave forcing to only one force, which has the direction of the wave direction. And then we split this only one force in the two direction, characteristic direction of the ship, the longitudinal direction and the transversal one. Okay? So it's a very, let's say, a very rude simplification, but of course it allows us to simplify the problem. Okay? And now keep in mind that these two forces are applied to this. Basically, this force is applied to the center of gravity of the immersed area of the ship. These two forces, the transversal one and the longitudinal one, are applied in the center of gravity of the transversal and longitudinal area of the ship. Or we may say that the result of the composition of these two forces, because we said that the wave forcing is reduced to only one force, which is split in these two directions. We may say, at the same manner, that the only one force resulting from the action of waves is applied in the center of gravity of the immersed area of the ship, projected on the perpendicular plane to the wave direction. Okay, so basically you have one force that is hitting a ship, and it's applied in the center of gravity of the immersed area, which is projected in a perpendicular plane. Perpendicular to what? To the wave direction. So what is the result of this? The result is that you may have, due to this forcing, you may have also a rotation, because as we know, the ship rotates around the pivot point. So if the point of application of the forcing is eccentric with respect to the pivot point, we get rotation of the ship. We get movement in the direction of the wave, and then we get rotation. Okay, this is our way to simplify a very complex problem. What should you remember? What should you remember for the exam? If you could remember one of these two, and they are the same formulation, you know, the only difference is sin square instead of cos square. If you could remember one of these two, along with the relationship for estimating the wind forcing, which I now put on the screen. It's this one. That would be great. Okay, and I'm not asking you to learn many things by memory, but unfortunately, you know, here we have to remember the concepts, and the concepts is something that it can be in a way absorbed by reasoning, but also we are talking about empirical relationships that in this case we use to simplify the problem, and I'm sorry, I think some of them you need to remember. Okay, and if you have any question related to this, also to the questions for the exams, possible questions, keep in mind at the end of the course I will make you a list. I will give you a list of likely questions for the exam. And but if you want any clarification, any further clarification, please ask. And remember that one thing is to study for the exam, and another thing, more important, is to study for getting, absorbing, and getting a knowledge. And I highly recommend you not to forget about this, because in a way what it means, what it counts later on is your knowledge. It counts more than the vote that you, the mark, the final mark of your degree. So be sure that you get the knowledge. I hope that I give you the means for getting it. I hope that my explanation is sufficiently clear, but if there is any reservation on that, any doubt, please approach me and let's discuss. It is difficult in a virtual environment, because when I am in a room, I look at your eyes and I think I have the capability to perceive if you got the concept. In a virtual environment, it's more difficult, and so I am always doubtful about what is the best way to teach in these conditions, and if you have an advice for me, I really appreciate it. And you know, this is the second year that we are teaching virtually, and in the first semester, last fall, during the last fall season, I actually taught in physical presence with a limited attendance, but I realized that even with the limited attendance, the interaction with the students allows me to be more effective. And when it's fully virtual, it's I had this experience last year for the first time. Now it's the second time, and I think I still have to learn. So I think we will teach in virtual mode forever, because I think it's a good opportunity. And I think the best way is a mix, physical presence and in streaming. But still, I think I have to learn something. So if you have any suggestion, and if you don't understand, the fault is mine, it's not yours. So if you don't understand, if you have difficulties to follow, if the teaching is boring, it's my fault, and let me know. Okay, now with the wave forcing, I think we are done. Okay, we are done. Here there is a chapter dedicated to a short chapter dedicated to resonance. It's a deeper discussion of what I already anticipated to you, because of course this, I mean, if I go back to the relationships, these relationships here, they don't take into account resonance at all. So they simplify a dynamic problem to a static problem. You see, this is these two relationships translate an oscillation into a constant forcing in two directions. And of course, it's a simplification. And then let's keep in mind that if you have an additional complexity, like for instance resonance, these are not taken into account by these relationships. Or let's say there are these two coefficients, the water plane coefficient and the depth coefficient, that in a way take into account, they increase the forcing by taking into account through an empirical approach what may happen. But it's not an exhaustive description. I mean, this is an empirical description. So let's discuss a little bit more what is resonance, and because resonance is extremely dangerous. It has caused the unmooring, the breaking of the mooring lines of ships, of even large ships in particular conditions. So it's something that we have to take into account. And again, the best way to take into account it is through lab experiments. So long waves, which we also call, which we also identify with the term waves of long period, which is more precise, but we can abbreviate it in long waves, are those characterized by periods longer than 20-30 seconds. We already talked about this range, 20-100, 20-40, and these waves, you know, once they enter into the harbor, they may induce singular conditions. And we are particularly concerned by two types of resonance. The first one we already discussed. It's the resonance with the characteristic period of the ship. Okay, and that's fine. But there is a second resonance, which is the resonance with the characteristic period of the harbor, because harbor areas have themselves a characteristic oscillation period. Let's suppose that you have a flat sea in the harbor, okay? And let's suppose that you suddenly take this water and bring it up, like for instance, like the examples that I made for the ship before. Let's suppose that you have a single wave getting into the harbor. It's just one wave that then brings up the water level in the harbor. It's only one wave. And then you, for a certain period, you have the water in the harbor that goes up and down, okay? And this is, this up and down has a characteristic period, which is the characteristic period of the harbor. And then, of course, if you have the waves that get in resonance with this characteristic period, what may happen is that waves are amplified into the harbors instead of being attenuated, because this is usually what we aim to get into an harbor. We aim to protect the harbor with infrastructure to attenuate the waves. But in some cases, we may end up with an amplification. And therefore, we have to be careful about this. Again, it's not easy to estimate the oscillation period of an harbor. It's, again, usually done through a lab experiment. In a lab, it's very easy, because what you do is just to bring water into the harbor, and then you release a gate in order to induce a sudden down movement into the harbor, and then you close the gate, and then you have this kind of wave, internal wave that is originated, and you study the period. But and also, you know, we have to be careful about the interaction between the characteristic period of moored ships, and in particular the surge, sway, and yaw periods of moored ships. And so this is something that, you know, you have to take into account, especially if you deal with a wave forcing that has a may have a long oscillation period. And it's something that usually it happens in particular places and particular seasons, only in certain seasons. Okay, and then there is a short discussion that suggests you to take into account also to take into account the direct forcing of waves against the berth, especially if the berth is a solid berth and not an open one with vertical walls. And with these vertical wall structures, you may have wave breaking against the vertical wall, which can induce a significant forcing. Here you have a rule of thumb, an order of magnitude. It can reach something like 600 kilonewton per square meters, which is, I mean, it's a considerable forcing. And this is something that acts directly against the berth. And it's a forcing that may be used not for estimating the mooring forces, of course, but for estimating the berth, the structure of the berth. Okay, loads by currents. It is something that it's usually discussed when estimating the mooring forces. So we discussed about wind, we discussed about waves, and then there is also the load by currents. And so how can we have currents into a port, into an harbor? And usually the harbor is a sheltered area, it's a protected area. So what are the conditions that may induce some currents? First of all, these are more frequent in large harbors, of course, and harbors that are exposed to the harbors that have a direct exposure to the seafront. So we may have wind forces that originate currents, and we may also have currents originated by gradients of temperature and salinity. Because if you have these gradients of salinity, increasing salinity means increasing weight, specific weight of water. So if you have gradients of salinity, then a water movement is originated because you have different weight of water. So if you have the same level of water with different salinity, then there is a different pressure in the surface of separation between the two salinities, and then you have a movement of water, because different pressure means that you have a movement, a translation of water. And also there might be tidal effects and river flow from estuaries may originate currents. Now, what kind of forcing may produce a current against a ship? Three types of forces. Pressure forces, because of course you have pressure of the current against the ship. Drag forces, drag means friction, okay? And forces induced by dynamic instability. What is dynamic instability? I mean, it's given by a lateral oscillation that produces the so-called flutter effect. Flutter is a dynamic instability of an elastic structure in a fluid flow caused by resonance, again, between the force exerted by the fluid flow and the deflection of the body of the ship. Now, this dynamic instability, you can think of it like the action of a current that generates an oscillation of the ship, and if the current is, the forcing of the current is periodical, then you may have this dynamic instability. And let's say that the friction forces are usually neglected, and except when you have the current that is flowing along the longitudinal axis of the ship. In this case, you have a reduced pressure because, for instance, the current may hit the ship on the bow, so there is not much pressure because there is limited area of the ship perpendicular to the direction of the current, but there is limited pressure, but there is a long side of the ship, so a large area of the ship in the longitudinal direction interested by friction. And so this is one case where the friction force may be influential, important with respect to the pressure. In the other cases, usually it's the pressure that matters. So, for the purpose of design, again, the resultant forces can be simplified into one horizontal force in the longitudinal direction and another in the transversal direction, and a vertical axis moment, all of them applied at the ship's center of gravity. And so again, in this case, we don't go into the details. There are empirical relationships which you may find in the Ports Designer Handbook that allow you to estimate, basing on the velocity of the current, allow you to estimate the resultant forces, the two resultant forces, like we did for the waves. But in this case, I didn't want to go into details because I don't think it is useful. I mean, these are other empirical formulations. If you need it in the future, then you can look at the Ports Designer Handbook or look at other technical guidelines that you may find for the place of interest. Now, let's say that that's it. I mean, the last thing that I can say is that when you have to design a new berth structure, if you have flexibility in the design, of course, it is recommended to make sure that the berth front is directed as parallel as possible to the prevailing current, you know. And so you need observation of currents. You need to, of course, to decipher what are the behaviors of currents, and then the suggestion is to make the berth front as parallel as possible to the current. Okay, and Oh, sorry, I forgot. These are the empirical relationships, but which I reported here. Sorry, I forgot because in a first edition of these notes, I decided not to bring them. Here, I decided last year I decided to list them, and you don't. In this case, you don't need to learn them by memory. And here you have also rotation. Okay. A rotational moment, you have a formula for estimating a rotational moment, but it is just estimated, the rotational moment, it is just estimated by multiplying the resulting force in the transversal direction times the, how to pronounce it, eccentricity. And the eccentricity is determined by multiplying the length of the ship, characteristic length of the ship, by, we multiply the length by an eccentricity coefficient. Okay, in fact it is described here. KEC is the eccentricity, or I don't know how to pronounce here, or how to pronounce it, or yeah, okay, I think you understood it.
It's eccentricity.
Eccentricity, thank you very much. I think you understood it. And then there is a value arranged for the eccentricity. Okay. And again, I go up. I don't go into the details. Basically, these are, you know, transversal component, longitudinal component, and rotational moment. And here you have again the specific weight of water, the gravity, and then here you have specific. This is the current of the velocity of the current, which is square, and then this is the area, the transversal and longitudinal area of the ship. They are very simple, but again, don't. And here you have a coefficient. I think. I don't remember, let me see. It's a shape factor, yes. And so a coefficient. And I don't think it is necessary that you learn them, okay? But again, if you wanna, these are taken from the Spanish standard, not from the port designer handbook, but I am pretty sure that also the port designer handbook has other relationship to suggest. Again, these empirical relationships are based on local guidance. Okay, there is just a very small, very short mention to the impact. And because when you design a berth, you have also to take into account the possibility that there are impacts between berthing ships and the berth structure. And there are several approaches for computing this kind of forcing, which are based in general in the computation of the kinetic energy of the mooring ship, and then this kinetic energy is transferred into impact force. It's a very simple law of structural mechanics that I think you know. It's transforming the energy into an impact force, and of course you may take into account that the attenuation due to the presence of fenders, and this you can find empirical relationship for estimating these impact forces. And you can find them in the port designer handbook, and I also think the Spanish standard give this relationship. In this case, I am correctly saying that I didn't want to include these relationships here. Overall, we completed this lecture on the estimation of mooring forcing. And we discussed, again, wind forcing, wave forcing, current forcing, and impact here. And unfortunately, what we can say is that the whole process is usually managed by using empirical relationships. It is something that often happens in several branches of engineering, and because the purpose here is to simplify a complex problem when we can do that, when we are allowed to simplify it. If we are not allowed, then there are numerical modeling and lab experiments that may allow us to make a more refined assessment. And I mentioned very often the lab experiment because this is what is most frequently used. Now, I say unfortunately because when we base our learning on empirical relationship, we should never forget to understand what's behind them. So this is why I dedicated a lot of time to discuss the physical behaviors of these processes, resonance, and I also spent some time to remind you about the complexity and to warn you about the complexity of the problem. And this is because, in order to get, again, a full understanding of what's going on, we need to keep the physics into account. So when we use physical approaches, like in structural mechanics, very often when designing buildings, we refer to the laws of physics and we apply the law of physics directly. And in this case, of course, it is easier to see the connection between the physical properties of the system and the operational design. When to simplify the problem, when you use empirical relationship, this connection may be lost. And I really want that you don't lose the connection. Again, I really think that a good engineering, a good design is supported by an understanding of what's going on. And then this understanding may lead you to use empirical relationship, which is fine. But on the other hand, we shouldn't forget what is behind the scene. And you may run the same risk when you use softwares for making a design. When you use software to make a design, it is very attractive because you have something already prepared. Think, for instance, at our exercises. We will make an exercise in the next 2 hours of lectures. And think about these exercises and think about the situation when you use a code that was prepared by me. What is the risk? The risk is that you merely apply the code, you blindly apply the code, and then you forget what is behind the scene. And it is a kind of risk that today is very relevant because today very often we use the pre-prepared softwares or commercial software to make computation. It is what I highly recommend to you is to, even when you use something that is already pre-prepared and very widely tested, try to understand what's going on, because this understanding allows you to make a final assessment of the validity and reliability of your design. If you just press the enter button and you cut and paste the number from the commercial software to your final report, technical report, without making an assessment, without making this type of assessment, which is, in my opinion, an essential ingredient of engineering. Like, you look at the result and you think, okay, this is fine. This is credible, this is reliable, this is something that I trust. And this final assessment is based on your knowledge. And some people say it's based on experience, but experience is a synonym of knowledge. And your knowledge, it's obtained by understanding and nothing else. There is understanding. It's the key. and there is no magic recipe. And the magic recipe is just understanding. Okay, and
excuse me, Professor, I have a question on the accidental impact of chips. Is it usually designed the impact of chips with the design wave, like the maximum design wave, or is it like just the impact of chips alone and the design wave is another load pattern?
Yeah, okay, this is a very good question. You are talking about concurrency of several different forcing, if I well understood. First of all, just take into account that when I said that the impact of ship is estimated based on the kinetic energy of the ship, the kinetic energy I'm talking about is originated by the mooring movement of the ship. So you estimate the kinetic energy by taking a ship velocity, which is usually adopted when mooring. So it's something that estimated in the presence of calm water, okay? And then you are right in saying that if you have another forcing like waves, it's more likely that there is an impact. So basically, the impact is given by the same forcing because waves are not increasing the velocity of the mooring ship. The waves just make the impact more likely. And therefore, we have to estimate this concurrency factor, which is, should I sum up the two forcings or should I consider them separately? Now, concurrency factors are usually suggested by the technical guidelines. So the technical guidelines, for instance, tells you that you should take the load originated by wind forcing, not contemporary to the load originated by wave forcing. They say that there is a concurrency factor to be applied to one of the two forcing, which is a reduction factor. Like, for instance, some guidelines say you can take wind forcing, the entire wind forcing plus half of the wave forcing. And in the case of impact, probably they will tell you that you have to take the impact forcing plus a fraction of the wave forcing, because you have to take into account that when there is the impact, the ship, it's only partially moored, it's not completely moored. And then there are these concurrency factors to be considered. And I think they are discussed somewhere in this page, and let me just have a look to it, because I don't remember what is the examples that I made. So I am sure, no, it's not in this page. I am sure that in some pages I discussed it. I gave an example, because if you look at the Ports Designer Handbook, it gives you some recommendation. The Spanish standard gives another recommendation. I am sure that, let me check, because in one of the lectures I discussed them. I don't remember. So, Paul, let me see here. Concurrence, because I'm not sure if I called it. Okay. Okay, let me show you. I go back to the previous lecture. The previous lecture was this one. Port planning and environmental impact. And here I am searching for concurrency. Here they are. Now, loads can be divided into normal loads and extreme loads, also called etc. And here we have the discussion on the concurrency factor. Extreme loads may be due to unexpected impacts from vessels, and this is the impact of ships that we discussed before, seismic activity, heavy storms, and so forth. Again, this is the previous lecture. Therefore, reduction factors, concurrency factors that take into account the likelihood of extreme loads to occur simultaneously are usually introduced, so that the extreme forcing are not merely summed up. So I think here, guidance on how to estimate extreme loads, normal loads, and concurrency safety factors are given by standards and guidelines and sometimes by local regulation in force. And national standards are considered the straightforward way. And again, if you look at the Spanish standard and the Ports Designer Handbook, you find some guidance on that. I didn't go into details because it's very local, very regional. I hope I answered your question.
Yeah, thank you.
Okay, I think that now we can make the 15 minutes break because then I want to start. I just tell you what I want to do later in the next couple of hours. I'm not sure if we will need the full 2 hours to make this. Probably yes. Otherwise, if we finish before, if we finish earlier, I will start the next lecture. But what I would like to do is this exercise, computation of wind actions on a moored ship and computation of mooring forces, which is interesting because it's a mixed exercise lecture, okay? Because it is basically a lecture on the mooring lines, how to displace them, and how to compute the mooring forces, which we didn't discuss in detail, which is a problem of structural mechanics. You have a moored ship, and you see this figure, and you have mooring lines. For instance, the red ones here. You have a wind forcing over the ship, and you have to compute the individual forcing on the mooring lines, which is something that we are not discussing in detail because it's a structural mechanics problem, but I would like to give you an example of application. So it is an exercise, but actually it's also an opportunity to discuss some issues that I'm not discussing in the lecture, but I am discussing here. Okay, so this is our next effort. Let's say that we meet at 11:30, okay? So a little bit more than 15 minutes. Thank you. I'm not stopping the video, so I don't forget to restart it. And so you will get a 15 minutes break into the video. Okay. See you later then. Thank you. here I am. Now, let me share the screen. Very good. I just want to spend some time to look for a video and a video of a lab experiment. And I found one that I would like to show you. Just 1 second. This one, it's taken by, let me just move this window here. This one is taken by Deft Hydraulics, and it's an experiment which is not really referred to an Harbour. It's it shows the wave generator that they have, but it generates waves into a flume, not into an Harbour. I think it is nevertheless interesting. They also have videos on wave generators into small-scale Harbour models. But I think can you please tell me if you can hear me?
Yes,
in the chat.
Well.
Okay, thank you very much, because I have sometimes a microphone that gets deactivated. So this is interesting because this is the largest wave generator in terms of height of generated waves available today, and it's a relatively recent facility. It was built, it was activated for the first time 5 years ago. I just want to show you how it works. Let's see if the video can be, yeah, I think it goes well. Just 1 second, because now it's starting generating waves. And the purpose here is to study the impact of these waves against a barrier. The barrier is located at the other side of the flume. And you see that it's a relatively long period. And now the wave generator is increasing the wave height. And the wave height is expected to reach the full height of the wall. I had the opportunity to assist at one of the first tests that were made. I was there, and I can tell you that it's really impressive, because if you look at the dimension and you compare the height of the two persons, and you can see that the overall height of the wall is something like 6 meters. And also you see that the waves are partially reflected by the barrier. And now, okay, and now it's, let me see this one, because this is a detail on the wave generator. It's seen from the other side, and here you see the full height of the wall that is reached by the waves. It's really impressive if you are there, because these are waves that have a wave height of, as I said, about more than 5 meters. And you see on the other side there is a barrier that is partially reflecting the waves, and you see that they are breaking because they reach the full height of the wall. And this is a nice example of a small-scale experiment. But of course, you see that even if it's a small-scale one, the facility that is required, it's an important facility. It's something huge. And as I said, they also have nearby a pool, which is used to study the dynamics of waves into harbors. This is a flume, so it's a different application. But if you look on the web for these videos, you find a lot of them. I just found these two with a very quick search. Okay, now let's go back to our exercise. And okay, let me close this. Just 1 second. Okay. Okay, very good. Now let me just 1 second, because I have to stop these videos. Perfect. Okay, very good. Now let me go Let me move this window and share the other one. Okay, so let's look at our exercise, and let's also launch an instance of RStudio. I hope I have, let me open, I hope I have it here, because otherwise I need to install it, but just 1 second. Okay, I have it. So I also launched just 1 second. I need to, because it is trying to open. Okay, very good. And yes, very good. Here I am with RStudio, but let me look at the exercise first. So, computation of mooring forcings. Let's look at this exercise. Let's read it. A ship with a displacement of 3,350 tons, a waterline length of 117 meters, a draft of 5 meters, a beam of 12 meters, pivot point located at 55 meters from stern, and side projected wind area of 950 square meters, is moored to a berth with 6 mooring lines displaced as in figure 1. Red lines, so in figure 1 we have to look at the red lines. The yellow lines are additional ones that are shown for the sake of illustrating further possible lines. So let's look at figure 1, red lines. Just 1 second, figure 1 is here. Okay, so this ship is assumed to be moored only with the red lines, and the pivot point is located where you see there. Let's identify with the y-axis the transversal direction, and with the x-axis the ship center line or longitudinal direction. Now, the additional mooring lines are here are shown because usually with a ship of this kind of tonnage, you use more than 6 mooring lines. I already suggested you to go, if you have an opportunity, sorry for this. If you have an opportunity, I already suggested you to go in a port and see how ships are moored. Sorry, this is RStudio who is popping up. Let's go back here. And so again, usually for a ship of this tonnage, they use more than 6. I reduced the number to 6 for simplifying the computation, because our purpose here is twofold. First, we have to compute the wind force. And then once that we have an estimate of the wind force, which is applied on the center of gravity of the side area, we have to compute the mooring forces. And in order to compute the mooring forces, you see that I consider only the red lines, and I give in the exercise coordinates for the bollards, which are named with the symbol B. So we have 6 bollards, B1, B2, B3, B4, B5, B6. And then I have 6 chocks. What are the chocks? 1 second. I show you what an image of a chock. It's also, I look on Google, chock ship. And let's look for the image, and let me put it on the screen. These are the chocks. The chocks, look at this one here, look at my mouse. It's the point where the mooring line passes through the side of the ship. So the mooring line is not binded around the chock. It's just a passage through, okay? And just to make it clear, the bollard is instead this one. Okay, let me see, bollard ship. It is this one. It is the bollard is typically on the berth. We call it bollard when it is on the berth. And instead, look at this picture here. Just 1 second. Here you see what we call the bitts. The bitts is the anchorage point of the mooring line into the ship. And you see that the mooring line is passing through the chock. So what I give for each mooring line is the coordinate of the bollard on the berth and the coordinate of the chock. Okay. Another thing that we need, Another thing that we need to know is the distance between the chock and the bitts, because it allows us to compute the total length of the mooring line, which we need to know because it's essential, because the longer the mooring line, the more elastic it is. Okay, I think I can now bring this on the other screen and focus again on the ship. So I have the coordinates of the chocks and the bollards, and also I am given, you will see in the text, the total length of the mooring lines. Of course, I can estimate through the coordinates the length of each mooring line from bollard to chock, and I will be given also the total length. Okay, and for computing the mooring forces, I don't need to know the coordinates of the bitts. What matters is the position of the chocks relatively to the position of the bollards. And what matters is, again, the total length of the mooring line, but it doesn't matter the coordinate of the bit, which is the ending point of the mooring line on the ship. Okay, let's go back to our description. So, figure 1, red lines. The ship is subjected to an extreme wind velocity of 50 knots, which is equivalent to 92.6 kilometers per hour, with wind direction perpendicular to the ship center line, which means that this is a simplified situation. If the wind direction is perpendicular to the ship center line, we have only the component along the transversal direction of the wind forcing. We don't have any component of the wind forcing along the longitudinal direction. So this is a simplified situation, okay? The ship is moored again with mooring lines composed by 3 ropes of cross-sectional area of 30 square centimeters each. This is a typical situation. Look again at the figure here. You see that the mooring line, which looks like a unique rope, actually is given by the composition of more than one rope, and they are joined together, okay? And this is in order to increase the resilience of the mooring line, because of course if you have only one body of rope with the same cross-sectional area, if this unique body gets damaged for some reason, then the damage may rapidly extend to the whole cross-sectional area. If you join together several ropes, then of course it's more resilient, because if you get one of the components damaged, then it's not automatically extended to the other ones. Very good. So this explains why I say that it's moored with mooring lines composed by 3 ropes. So the total area, cross-sectional area of each mooring line is 30 times 3, 90 square centimeters. The elastic modulus of each rope is 125 kilonewton per centimeter square, and the breaking tension is 25 kilonewton per square centimeter. So I think that you had some courses of structural mechanics. So I assume that you know what is the elastic modulus and what is the breaking tension of a given material, okay? And of course, the breaking tension is given per square centimeter, which means that in order to get the breaking tension the breaking force of each mooring line, you have to multiply 25 times 90, and then you get 90 times 25 is let me see, 2,350 kilonewton, which is the breaking force of each mooring line. Why do I need an estimate of the breaking force? Because once that I estimated the mooring forces for each mooring line, I have to check that the mooring force is well below the breaking force for each mooring line. I hope this is clear. And let me check on the chat if you have any question. Okay, and the elastic modulus is important because we need to estimate the elasticity of each mooring line. Again, I assume that you know what the elastic modulus is. If you have any problem with this, please let me know, but on the other hand, if you have any problem, I would suggest to you to go back to your studies of structural mechanics first, because it's something that we are not supposed to discuss here. Now, what we have to do? We have to compute the wind force and the yaw moment, first of all. And the yaw moment is the moment around the vertical axis of the ship. And this is something that we need to do first, computing the wind force and yaw moment. And basically, the wind force is to be estimated by using the empirical relationship that we discussed. So let's forget about wave forcing. We have only wind forcing here, okay? And then we have to compute the mooring forces and the safety factors for mooring lines by assuming that the ship is moored with the 6 mooring lines that are depicted in figure 1, by assuming again that the origin of the axis is placed over the pivot point, and assigning the following values to Bollard and Chock's coordinates, where x is along the ship center line, as we discussed, and y is along the transversal direction, as we discussed. So let's look at the figure again, and let me just do this. Just one second. I open the figure in another window so I can depict it on the screen together. Just one second. It's here. Sorry, view image, okay, and let me bring it here, okay. So let's look at this part of the picture. So for instance, let's look at B1. B1 is the Bollard number 1. The coordinate is -50 on the x direction, so on the longitudinal axis, and -10 in the vertical axis, y direction. So vertical axis on the figure, actually it is the transversal axis on the ship. So these coordinates are referred to the origin located in the pivot point, which is the red point where I am placing my mouse now. This is the pivot point of the ship, which is located as described in the text, and precisely, if you remember, the text says that it's located 55 centimeters from the stern. And in fact, you see that Bollard 1 is placed as a coordinate of -50 because it's very close to the stern. Okay. So these coordinates again are referred to the pivot point. It is extremely important that we, of course, when we give coordinates, we specify the system of reference. Very good. Now let's go down And to make the computation, assume that the mooring lines are horizontal, so there is no inclination with respect to the vertical direction of mooring lines. It is, if you want, it is a quite unusual situation because bollards are located at the elevation of the berth, while the chocks are located at the elevation of the deck of the ship. And usually the deck is higher than the berth. A situation where you may have the chocks at more or less the same elevation as the berth is, for instance, a cargo. With cargoes, sometimes the deck is not elevated with respect to the waterline, or it's just not much elevated. And this is a possible situation where the mooring lines may be more or less horizontal. Otherwise, they are inclined at an angle in the vertical direction. And let's ignore it because, of course, if they are not horizontal, the computation should take into account also the inclination of the mooring lines. In this case, the mooring lines are horizontal. The coefficient CW, which is used to compute the wind forcing, is 1.3. And here is another important specification, because I told you that we need to know the total length of the mooring lines. So it is suggested here, it is prescribed here that mooring lines are 50% longer from bitts to bollards than the distance between bollards and chocks. Okay. And then check that safety factors for the mooring lines, for the composition of the three ropes, it's always greater than 10. Okay, so once that we computed the mooring forces, we know the braking force of each mooring line, and we need to check the safety factor. Very good. Now,
excuse me, Professor.
Yes, please.
Why do we have a very large safety factor? Because usually we have 2, maximum 3 in structural engineering. So
yeah, in structural engineering, yes, but for the mooring lines, usually it's adopted a very large safety factor, because the reason is that, you know, it is a process that it's subjected to large uncertainty. And think at, for instance, the computation of the wind forcing and the wave height. It's something that there is a lot of uncertainty in there, so you have to be prepared also to a situation that you didn't predict. And also there is to say that mooring lines, ropes, are usually subjected to some kind of deterioration. And therefore, it is suggested that the safety factor is larger. It is the same thing for the ropes that are used for instance, for rescuing people from the helicopter, or I mean, you have to be really sure that they are oversized. And there is also another thing to say, that to oversize a mooring line does not require a much larger additional expense. It's not like for a structure where if you oversize it, you have construction costs that are much larger. In this case, it's not a big problem. So this is why the safety factor for mooring lines, it's always suggested to be quite large. Okay, now I hope I answered your question. And
it's clear, thank you.
Okay, perfect. And in general, keep into account that safety factors in engineering are suggested by taking into account the possible consequences of a failure, and and the uncertainties. So if you have a large uncertainty, it's of course you need a larger safety factor. And if you have awful consequences, for instance, when designing dams, you use a large safety factor. And it's not just enough to take for a dam 1.5 or 2. Usually it's taken a safety factor that it's much larger. And the same thing here, because, you know, if you get, think of a ship, a moored ship, and think of mooring lines that break, you know, it's a very dangerous situation. Think of a ship that is loading people, cars, or I mean, in any case, loading. So there are people working to load it, and you absolutely have to avoid that the ship gets unmoored suddenly because a mooring line breaks. And also you have technical regulations that impose to change the mooring lines at a periodic frequency. So you cannot use the same mooring line for 50 years. And this is another thing that you may look at if you go in a port. Look at the state of mooring lines, and you will see that in normal condition, you don't see mooring lines that are very deteriorated. Now, here there is a box that discusses about the displacement of mooring lines, and I think it is useful before starting with the exercise that we read these, because this is something that we don't talk about in the lectures. It's, I mean, it's something that it's unlikely that I ask at the exam unless you are very well prepared. But I think that because, you know, it could be a question for the laude, maybe, you know, because it's not a usual question. And but I think they are also interesting. I mean, it's interesting to notice what is the reasoning behind the search for a very safe condition. I think it is really interesting to look at them. So, first of all, the least possible number of mooring lines shall be adopted to simplifying mooring maneuvers and tensioning. And I think this is very clear. So, without reducing our safety, the simplest, the better. Okay? The simpler, the better. Now, the mooring lines and the fenders should be symmetrically distributed with respect to the center of the ship. And the center of the ship is to be intended as the center of gravity. Okay? The objective is to distribute the loads homogeneously among all the moorings or fenders and reduce the coupling between different movements. For the calculation, it is usually assumed, here there is a spelling error, there is a double is, it is to be read it is. Assume that the mooring remains tensioned at all times. This means that when you moor a ship, you shouldn't have mooring lines that are untensioned. Okay, this is extremely important. And which means that you have to use mooring lines and fenders in a proper way. Now, the mooring lines shall be laid as horizontally as possible to reduce the force component. A simple reasoning of structural mechanics suggests you that the higher the inclination and the higher the forcing. I mean, think of a mooring line that runs vertically and is subjected to an horizontal forcing, because we are talking about wind forcing is horizontal. An horizontal forcing translates in the vertical direction, if I have only vertical mooring lines, in an infinite forcing. So the higher the inclination, the higher the forcing. Okay. The max vertical angle should be, another spelling error, 25-30 degrees in the worst loading condition and water level. Now, give me 1 minute because I want to correct this spelling error just now, otherwise I run the risk of forgetting. So it is, And I'm correcting on my official web page, not on the mirror. So should be 25, 30. Okay, these two are corrected. Good. Now, of course, the degree, the inclination of the mooring lines depends on the loading condition. So we have to take into account the worst one, and also depends on the water level. So again, the worst condition is to be taken into account. Okay. Now, the mooring lines shall be laid out as aligned as possible with the movement they seek to restrict. Of course, because otherwise you have a component, it's the same reasoning as inclination. You have a component along a direction that is magnified if the mooring lines are not aligned with the movement they try to impede. You have a magnification of the forcing. Okay. For longitudinal mooring and continuous berthing lines, the optimum disposition of the mooring lines shall consist of head or bow, stern, and breast lines. We already discussed what breast lines are, but let me now show you the figure again. 1 second. Here it is. Now, the breast line is, for instance, the one connecting C2, choke C2 with bollard B2. And you see that it's symmetric on the other towards the bow. There is a breast line B5, C5. Good. And then there are the springs. The spring line are C3, B3, B4, C4. Good. So the breast lines and the head and the stern line should be drawn from the ship as close to bow and stern as possible. So let me show you again the figure. You see that the breast line is very close to, in this case, to the stern here, and the stern line is precisely located in the stern. And again, for the bow line B6, C6, it's located at the bow of the ship, and the bow's breast line, it's B5, C5, is located close to the bow. Okay, and now what about the springs? The springs are connected to the ship at bow and stern at distances which are more or less 1/4 of the length. And this is more or less what you can see here. It's probably not 1/4. You see C3, B3, it's not really 1/4. It's, but anyway, this is the indication. Now, 1 second. Okay, let me move this away. The bow and stern line shall be laid out forming an angle of about 45 degrees with the longitudinal axis of the ship. And this is something that it's not really, in my figure, it's not really met, okay? And let me show you the figure to better explain what I mean. So, for instance, here the yellow lines are not used in this mooring scheme, and the yellow lines are bow and stern line which have an inclination with the longitudinal axis which meets the requirement 45 degrees more or less. Okay. Here, to simplify the scheme, I am using the red lines which don't meet this prescription, okay? And let's say that in this case, the scheme I'm referring to, the red lines only, may be used in a very calm situation and for a limited permanence. But let's notice that in order to simplify the scheme, I removed here the yellow lines, which are an additional safety and are better displaced with respect to the red lines that I kept, okay? This is nothing wrong. Because we are talking about guidances, not prescriptions. But of course, they have to be evaluated. For instance, if you have a ship that is berthing for a very limited time, then it's in a calm, the sea is in a calm condition, no wind, then that's fine. You don't need to use 10 mooring lines all the time. Now, let me say something about, sorry, I'm trying to move this window away, about the breast lines, B1 and B6 in figure 1. They should be perpendicular to the axis. So what axis? And the longitudinal axis to the ship, but layouts with angles can be admitted, and in my case, I'm indeed using the angle. And the spring lines, B2 and B5 in figure 1, should form angles of 5 to 10 degrees. Other configuration, especially those that omit the breast lines, are also customary. As I said, I mean, other configuration are customary. It's no problem, depending on the given condition. Likewise, for large ships, spring line duplication can occur. In our case, doesn't occur. Located symmetrically with respect to the bow and the stern. And then, next one, the mooring lines of the same function, breast lines, bow or stern lines or spring lines, should be of the same material and of equal length in order to maintain the symmetry. Okay? Mooring lines should preferably be long and few and made of a material with high deformation capacity, elasticity, high elasticity. When significant movements are to be avoided, because elasticity brings with it the fact that the ship may move, okay? When you want to avoid movements, then galvanized steel, galvanized to avoid corrosion. Steel lines may be a more appropriate solution. There are situations in which you don't want the ship to move, absolutely. And then steel lines may be more appropriate in this case. But of course, you have to take into account that the elasticity is reduced. Optimal length of mooring lines varies from 35 to 50 meters according to the type of ship. Lengths of less than 30 meters generally are to be avoided because they have too low elasticity. Now, about fenders. The number and optimum separation between fender axes should be less or equal to 15% of the shortest length among the design ships, okay? Because fenders are applied, sometimes they are applied also on the ship, but they are also applied on the berth. And therefore you have to size their distance according to several possible ship lengths. And of course, the shorter the distance between the fenders, the better. And it is given this recommendation that they should be placed at 15% of the shortest length among the design ship for continuous berth fronts. The fenders should be positioned along the total length of the berth front. In discontinuous berthing configurations, discontinuous may imply that the berth is not continuous. It may be discontinued. And so if it is discontinued, then 2 fenders may be sufficient with the separation which is larger, of course. Now, let's look at the solution, and let's look at the questions that we have to resolve. Let me go up. We have 2 questions. Compute the wind force and the yaw moment. This is our first question, okay? So let's go to it. Solution. Now, first, there is an R code that I open in a new tab. Sorry, it's not available. Why is that? Let me check. Not found. This is fun. Let me see. And let me see, because there is a second code later on. Let me see if maybe not found as well. Okay, let me check where the code is, and let me check in the other web page. But I think that if it's not available on the mirror, probably it's not available even here. But let me check. And yeah, it's available here. Why? I don't know. Okay, let's see. Let me get it, because you will find it on my web page. I think there is a problem with the permission. So let me get the link from here, from my web page now, and let me open it with the text, or with the text editor. I would like to open it. So let me save the file. You should be able to find the link directly. And let me see, I open it with a text file. Give me 1 second. So here we are. Okay, downloads, mooring forces. And then let me, okay, very good. Very good. Okay, this is the R code. But let's, before looking at the R code, let me go back to the web page. Here we are. And let me go to the right place here. I clicked on the link here, the first link after solution. Okay. And then if you click there, you will be able to open it probably directly in RStudio. What I suggest to you is let's not open it in RStudio, because of course if you open it in RStudio and you run it, the whole code, you get the solution. But what I would like to do is to cut and paste from an editor, text editor, to RStudio line by line, because I want that we understand what we are doing. Okay. So let me open then RStudio at this stage. I had to open it again because it's for some reason it crashed. So let me see RStudio. Okay, let's hope that now it's okay. And let me open a new, I'm not sure whether I need a script, but yes, let me open a new project, new file, R script. So I get file, new file, R script. And I should get, I don't know why it didn't. There is something wrong in my RStudio today. It's again crashing. Let me open another instance. Don't understand why it's giving to me some problems. So let me try again. And maybe that I have to do one thing. I'm not sure whether can you still hear? Okay, can you still hear me, students?
Yes.
Okay, very good. I had the PC that paused for a while, so I was turning to the phone because I lost the connection for a moment. Okay, let's hope that now it's okay. So what I did is opening a new R script in this window, and it's let's save it because I want to make sure that I can save the script on my desktop. And let me show you what I did to save. What we can do is File and Save. And then let me save it on my desktop. I call it March 16.r. Okay, let's hope that it doesn't crash anymore. And let me give more room to the console. Very good. Okay, so we are ready to cut and paste into RStudio our exercise. And let's cut and paste into the script rather than directly on the console. Why I'm doing this? Because I want to save in a script everything I am doing. Okay, I mean, if I cut and paste directly in the console, it is still possible to save everything by saving the history. But what I want to do is to get immediately a script without the need of saving the history. And this is something that you have to do when you are making a computation in R, which you think you may need to repeat. So if you open R just for a very quick computation and something that you predict that it's a unique application, not something that you may need to repeat, then my suggestion that I give to you is to use directly the console without even opening RStudio. RStudio, it is useful when you start a project, something that you may need to save, and to save because maybe that you have to distribute it, or maybe that you want to repeat it, be able to repeat it. And in this case, then my suggestion is open RStudio, and when you use RStudio, in my opinion, you always need to make a script. Because if you just want to make a computation on the console, then just open the console. You don't need RStudio. If you open RStudio, it's because you have something that you know, it requires an interaction. It requires trials. It requires a graphic window, and then it's better if you save everything into a script. Okay, so let's start our exercise. And what is the first thing that we have to do? We have to memorize the coordinates of the bollards and the chocks. We have to memorize the input data. So we have some input data that were given by the exercise, and the most important one is perhaps the coordinates of bollard and chocks. And so let's memorize this data into R. And how to do that? We have to define variables or vectors which contain the coordinates. And in order to speed up the process, let's look at the code that I am suggesting to you. So let's make a cut and paste from the code to the script. Now let me go to the code then, which is open in my text editor here. And let's look at the first two instructions. So what are these? These are definition of vectors which or arrays with the coordinates of bollards and chocks. So the first line, let's copy it. Okay, copy. Okay, I selected it on the text editor. I right-clicked, copy. And then I change the window. I go to the RStudio window. And then I paste the instruction into the script. Paste. And then let's run it. I click on run or control enter, but let's click on run. Good. You see the console? I got the memorization of these coordinates. Are we sure they are correct? Yes. Look at the coordinates. These are the coordinates of the bollards. The bollards are placed at the same y coordinate and varying x coordinate. Let's go back to our text. And let me go to the coordinates. You see, bollards, same y coordinate, varying from -50 to 57 x coordinates. So let me go back to RStudio. And you see that the numbers are correct. You may say, why did you double check? Because it's clear that they are correct. We took your code. Yes, that's true. I double checked because I want you learn that every time that you put input information into a model, because we are setting up a model here. And when you put into your model data, input information, just double check that you are not making any mistake. Because as an engineer, the first rule for you is to avoid a mistake. Okay, very good. So what is CB? It's the coordinate of the bollard, and it's done through an array. What is the function cbind? Is column bind. It is binding two vectors, and you see the first one is the vector of the x coordinates, and the second one is the vector of the y coordinates. So this instruction binds, puts together two vectors to form an array. If I now write in the console, not in the script, in the console, because I want to check. I want to check what I have memorized, and this is the matrix. Again, note, I use the console, not the script, because this is a simple check. It's not something that I want to repeat in the future, okay? When you write a program, you have to be very rigorous and keep everything well ordered with a rigorous approach. The code, the resulting code must be very clean. Remember, when you write a code, after 1 week, you don't remember anything of it. So if you want to be more rigorous, even more rigorous, here in the script, put a comment, an hash, and then you write coordinates, or better, CB is the matrix of the coordinates of bollards. Now, clearly, commenting takes time, but commenting allows you to save time when you go back to a code that you have previously written. Again, I tell you, when you write a code, you get the feeling that you will forever remember what you're doing. The reality is that after 1 week, if you are a busy person, you forget about it. And there is nothing more complicated than understanding a code that was already done, even if it was done by you. So on the one hand, commenting takes time. On the other hand, commenting saves time. So you have to look for your optimal compromise. Every one of us is different from others. So you have to understand what is the optimal level of commenting in order to, at the end of the story, save time. Okay? If you don't comment at all, you lose time. If you comment too much, you lose time. There is an optimal combination, which is very personal, very individual. And I insist, to make a good engineer, you need knowledge and you need efficiency. And I mean, in Italian we say, there is a proverb who says, preste bene non stanno assieme, which means that you cannot be quick and efficient at the same time. Sorry, quick and rigorous at the same time. Actually, I think it is not true. A good engineer is quick and rigorous. But you have to find, of course, your personal optimization of your organization. And again, it's something that makes you more competitive if you are well organized. Okay, let me go back to the code and let's take the second instruction, which is the coordinates of the chocks. Copy with the right and then paste here in the script, and then let me run it. Run. Good. Shall we make a comment here? Okay, let's say no for now, because it's clear that to me, it's clear that if the first line is coordinates of bollards, then the second line is coordinates of chocks. But you may decide to put a comment. It's up to you, okay? Now, let's, I put a blank line here just for my personal organization, and let me save it, okay? And more rapidly, Control S, okay? Once in a while, save it. Okay, now, let's go back to the script. And here you see that there is something new, function. So what is this function? Because it's a function. You see that it takes argument between round parentheses, so it's an R function. What is this function called function? This is a new thing. So let's take some time here. This is an instruction which allows me to build a custom function in R. Okay? And let me give you an example. So, in order to give the example, let me open a new R console. This is a new console, okay? Why I'm opening a new console? Just because I don't want to interfere with what I'm doing with RStudio. You can open several instances of R, and let me build a function to show you what I mean. So remember, what is a function of R? It's a pre-prepared task which makes something like the square root in R. It's a function that computes the square root of its argument. sqrt4 gives to me 2. Now, let's suppose that I want to build a custom function, okay? And let's suppose that the function is simply taking the sum of two numbers. So I want to give as argument of the function two numbers, and the result of the function is the computation of the sum. Okay, so let me call it Alberto, okay? Alberto is the name of this new function. And I can define it by writing Alberto is equal to function, and then between round parentheses, I give the arguments. And the arguments may be A, the first number to compute the sum, the first addendum, and then the second argument. And let's give a default for the second argument, okay? So the second argument, default value is 5. Now let me press return. You see there is a plus because R is waiting for me telling it what to do with this function. And let me open, because this is something that I need, let me open a curly bracket. Okay, curly bracket, I use Alt-GR, which is the key that is placed at the right of the space bar, and I need to keep it pressed, and then I hit the key with the number 7. And this is the curly bracket. Now, what I have to do is to list the instruction of the function. And then let me, very simply, computing the sum, I define a variable c, which is equal to a plus b. Good. Now, what do I want to get back from the function? It is to be specified with another function, return c. And then I can close the curly bracket, Alt-GR, keep it pressed, and then the key 0. And now return again. Now you see that I got back to the console. Let me clear the screen and let me just type Alberto to see what happens. And here I have my function. Now let's try to make Alberto 10. What do I get? 15. Because the first argument, A, I gave the value of 10. The second argument, I didn't give any value. And then it took the default. Another trial, I get back the previous one, and I give now a value for the second argument, Alberto 10, 7. 17. You see, I wrote a function. And when it is useful to write a function, I mean, it's useful when you think that you may prefer to execute a series of tasks with just one instruction. So in this exercise, I wanted to write a function in order to take the opportunity to instruct you on how to do that. Do you have any question? Okay, so let's close this new console. I close it without saving because I don't need to save it. And let me go back to my code. So, and now there is this function called moorings, which makes the overall computation of environmental forcing and mooring forcing for a berthed ship. You see that I put some comments here. Now, let me copy this instruction. Copy. I put it in RStudio. Paste. And then there is, you see, there is the script that went forward in the next line. It went forward because now it's waiting for a series of instructions to be placed into the function. And it went forward because it's a way to recognize what is included in the function. And look here, at the line 6, there is a warning, unexpected end. What does it mean? It means that the document cannot end here, okay? It's a synonym of the plus that you would get in the console. If here you run it, you get the plus. And in the script, you get a synonym, which is the warning, unexpected end. Now, in the console, let me cancel it, cancel the instruction, and let me clear the screen. Good. Now, here I have to write my function, and then, but before writing, let's look at the arguments that are placed here. And this is VW, I don't remember what is, and let's see in the exercise what is the variable that takes a value of 92.6. Let me check because I don't remember. And it's let me see. Okay, it's the velocity and the wind velocity. Yeah, perfect. I go back to RStudio then, okay? And in fact, it is VW, it's velocity wind. Side area, alpha, which is the angle of it's 90 degrees. It's the angle of the wind direction with the ship center line. And then there is the coefficient CW to compute the wind forcing, and the length of the water line, and the coordinates of the bollard CB, the coordinates of the choke CH, the cross area, and EI, I don't remember, I think it is the elasticity module. Yes, it is the elasticity module. And sorry, it's let me check what is 125, because I don't remember. Yeah, it's the elasticity module. Yes, the elastic modulus. And then there is the rope tension 25, which is to be multiplied by 3. Okay. Okay, now these are the arguments. The arguments are my input data, and I gave them as a default. But of course, if you want to change them into the function, you can do that later on. So that's perfect. Okay, let's go to the code and copy what follows. And there is the curly bracket, and then there is a comment. Let's copy everything. Okay, so I make the selection, copy. Very good. And then I go here, and with the right, paste. Okay. And you see that everything is shifted, but not the curly bracket, which is fine. I mean, because, this is an unexpected, unmatched opening bracket, which is fine, because it is expecting for the closing bracket. And then here, I don't remember, let's see, what does it say? I don't think this warning, it's, I don't understand. I don't think it is a significant warning. Let me go to a new line, and let's copy what follows. So, computation of wind pressure, perfect. So this is the computation of wind pressure. Okay, copy, paste. I think I used the same symbol that I used in the web page, but in any case, we can see that it's given by what I remember, CW times side area, and then there is the sin of alpha, which is 1 because the wind is perpendicular, and then it's squared, and then there is the density of air, the wind velocity, divided by 3.6 because it's divided by, I think it is I don't remember, but there is G at the denominator, and I need to look at, no, it's here, divided by 2. Okay, 3.6, it's, let us check. Let's look at the web page, just 1 second. So this is mooring. Okay, let's go here, and then it's forcing estimation. I don't remember this, sorry for that. You see that even my memory needs to be refreshed sometimes. But when I make the exam, I am prepared. I study the day earlier. You know, also professors prepare the exams. So the day, a day in advance, I get back to it. Okay, it's, okay, let me see. It's, I don't understand, because there is the density of air, which is 0.01225. Let me see what I did here. It's okay, square density of air, and then there is wind velocity. Let's see, wind velocity squared divided 2g. Let's look at what is wind velocity divided. Yeah, it's, let me see. Wind velocity is in knots, and it's given. Let's look at the exercise. It's wind velocity. Yeah, it's given by 92.6 kilometers per hour. So it's a conversion factor, because I need to translate kilometers per hour in meters per second. So what you see here, I go back to RStudio. What you see here, it's a conversion factor. Wind velocity divided by 3.6 to transform kilometers per hour in meters per second. And of course, you have to always make sure, this gives me the opportunity to remind you that you always have to be consistent with the units. So always make sure that units that you are adopting are consistent. And like gravity is given, of course, it's 9.81, it's meters per square second. So, of course, even the velocity has to be given in meters per second, while 92.6 is kilometers per hour. So 3.6, again, it's a conversion factor, and which derives from 3,600, which is the second in an hour, divided by 1,000, or 1,000, yes, which is the meters in a kilometer. Okay, very good. So this is the computation of the wind pressure again, and the wind pressure has to be completed, the computation. I go to the code with the computation of the rotational moment. And this is a pressure. No, it's not a pressure, it's a wind forcing. So let's change it, because this is a forcing, not a pressure. It's already multiplied by the side area. Okay, now let's compute the rotational moment. Copy. And let's go here, paste. And so I would change here not wind pressure, but wind forcing. Okay, because a pressure, when it's multiplied by an area, becomes a forcing, and we have to be very precise with the terminology. I will also change the code in my website. Okay, now the rotational moment, positive clockwise. This is given by the wind force times the eccentricity, which is given by the multiplication of the length of the water line by 0.04, which is an eccentricity coefficient. Okay, and then I put the negative sign because the rotational moment is positive clockwise. Okay, and so given the direction of the wind, I need to give, according to this convention, the negative sign. And this is our rotational moment. Let me now move forward with the computation. And this is the computation of the angles theta. What are the angles theta? Let me show you the figure. And the figure is, just one second, I see if I have already a figure. Yeah, it's here, just one second. I get, here I have the figure, view image, and just one second, I move it to your screen. So look at the angle theta, is the angle between each mooring line and the y direction. And it's positive, as shown here. So a negative theta means that the mooring line is in the left side of the vertical direction, a negative theta. A positive theta is like you see here, where the mooring line is at the right side of the vertical direction. So we now have to compute these angles. Let's go to the code. And first, let's define a vector of theta, which is now filled by zeros. And then for each mooring line, we can compute theta with this instruction, which is an inverse tangent of a combination, a function of the coordinates. Okay, and the coordinates of what? Of bollards and chocks. Okay, let's now copy it. And let's now paste it in our studio. Paste. Okay, good. New line. Now we are not computing anything. We are not executing anything. Let's execute this series of instructions, which I remind you aim to build a function. Let's run all of them all at once, okay? At the end, when I have completed the function, I will run the series of instructions to define it in R, okay? Before moving forward, let me save. So I go here in the script window and I press Ctrl S. Good. Let me go back to the code. We are almost ready. We have the computation of the length of the mooring lines. Again, this is given for 6 mooring lines. And so first I define a length from bollard to chocks, and it's called this variable LBC. I define this vector by filling it with zeros, and then I start a for cycle. I'm not sure if we talked the last time when I introduced R about the for cycles. And I think that even if I didn't mention, even if I already introduced them, let me spend a few words to make a recap. Cycles and conditions are the essential elements of a programming language. So when you learn a new language, you have to learn how to write cycles, how to use cycles, and how to use conditions. We didn't talk about conditions yet, but let me make a recap of what is how to write a cycle. A cycle is a repetition of tasks, like you see now on the screen. Computation of length from bollard to chock. This is to be repeated 6 times because we have 6 mooring lines. So it's a typical cycle. And a cycle in R is written by using the instruction for. It's a function, and in for has an argument. You have to give the counter variable, which is I in this case, and you have to define how many times the cycle is to be repeated. And you define how many times through defining through the definition of the range for I. So what you write is for, open the round parentheses, I in 1, 6. I in the range 1, 6. Okay? And this is what I am selecting now on the screen. And then you use the curly bracket to encompass the instructions that are to be repeated each time. And these instructions are, first, computation of length from bollard to chock. And this is the computation. It's just a trigonometric computation, okay? Given the coordinates, you compute the lengths. And then we compute for each mooring line the total length by taking into account that the total length is 15% more then the length from bollard to choke. So the total length LTOT is given by LBC times 115. And then we close with the right curly bracket, the fourth cycle. Okay? Now, just 1 second, I'm looking. Okay. Now let me copy this. Sorry. Copy this, copy. Perfect. Let's go to RStudio and let's paste it. Good. Now, our function is not yet completed, but you may say, first of all, let me save it, Control S. You may say, look, I still have the warning here, unexpected end of document. Why? Because it's not completed, the function. But you may say that at this stage you want to check if everything is working without waiting for the function to be completed. Okay? So this is what you usually do when you write a program. Make periodic checks if everything is working. And why should I make periodic checks? Because if you write a very long program, 10 pages and 1,000 lines, and at the end of the story you get an error, maybe that the error forces you to make a change in the first line of the program because this was the mistake. And maybe that by changing the first line, you need also to change the other lines. And this would be a problem because, you know, you have to correct 1,000 lines. So it's a good idea to make periodic checks. Give me 1 second because I am running out of battery for the phone and I use the phone to check what you see. So just give me 1 second, I put the cable, just 1 minute, one second. Good, the phone is breathing again. Just 1 second. Okay, and then let me, okay, good. Okay, so as I said, let's make a check. And how should we make a check? Okay, first of all, we need the right curly bracket, so Alt GR 0. And you see that automatically it went to the first column of the script because R recognized that this is the closing curly bracket and I don't have the warning anymore, which means that that's fine. I closed my function. I can end my document here. But let me tell the function to return something if I want to check. So let's write, for instance, and here I created a blank line, return. What should I return? I don't know. Let's return LTOT, okay? And let me save it. And now let's run the instructions that I didn't run yet. So all the instructions for the definition of the function, let me select all of them. Good. And then let's press run. Good. You see that in the console, I have everything that was run there. So let me clear the console Control L, and let me type the name of the function, moorings, and without parentheses. And I get back the whole function. And let me check it, okay? So I clear the console. I can write again moorings and no arguments. If I do no arguments, it takes the defaults, which are already there. So I should get an output from here. And this is my total length of the mooring lines. This is the vector of the total length, which means that the function is working. And I may check if, let me get the figure back. Let's check if this is consistent. So let's take this, this figure. And what I am expecting here is that the first mooring line, B1, C1, is shorter than the second. And the third should be, I'm not sure, it should be shorter than the second. I'm not sure with respect to the first. So let's see at the number. The first is 6.90. The second is 9.89, which is good because it's longer than the first. It matches my expectation. And then the third is 7.73, which is shorter than the second, and it's also a bit longer than the first. Which is fine. I mean, everything seems to be correct, and given that they are symmetric, in the second part of the vector, you see the numbers are the same than in the first part of the vector, which is fine. It seems that everything is okay. So what I did here, I did a perceptual assessment of the correctness of the result. And the perceptual assessment was based on a comparison with this figure here. This is precisely what you have to do once in a while. Check if the program runs well by comparing what you get with your expectation. This is how an engineer works. And this is extremely important. Sorry, I may look naive to you, but I think it is extremely important that you have clear what is the behavior that you should assume to minimize your risk, your professional risk. And this is the way to follow. Periodic checks by comparing the results with your expectation. Of course, you need to elaborate an expectation. In this case, it was very easy because I just had to look at a figure. In other cases, you may need to elaborate your expectation by making a prediction of what is the outcome that you are expecting from a computation. And this is what you have to learn to do, and you need the knowledge of the theory to do that, okay? Very good. And this was particularly important in this case because we are using a pre-prepared code. It may be incorrect. Nobody tests it. It's my code. I did it. And maybe some students last year, because last year was the first time that I used this. Okay? And you see that, for instance, I already identified a needed correction in a comment because I called the wind forcing, I called it wind pressure, which means that this is precisely the way you should learn to work if you didn't learn it yet, because you may say that, as I said, this is quite trivial. Okay, now let's go back to our script and let's delete what has been written just for the purpose of making a check. Okay, so let's delete the check instructions, or I may have commented them, your choice. And let's go back to the code that I have to cut and paste. And look, this code is moving forward in a unique solution to, because the wind forcing was already computed. It's here. The first question is already there. Okay. Okay, good. Now it's moving forward to the computation of the mooring forces. And before I move forward with the computation of the mooring forces, let me see, because I got already here, and from here on, so this part that I am selecting, in order to understand what's going on, it's quite short because you see that it's not long. Now, in order to understand what's going on, let's go back to the web page of the exercise. 1 second, and it's not here. It's here. Because computation of mooring forcing, I think, yeah, the R code is the same. And let me say that this computation belongs to the domain of structural mechanics. Okay, so here there is a description of what you have to do, but we are not going into the details. Okay, and here is the step-by-step procedure for computing mooring forces is articulated as follows. As I said, this is a problem of structural mechanics. You have a situation where you have a ship that is moored in this way, and you have a wind pressure acting along the y-axis, which is generating, which is to be decomposed along 6 elastic mooring lines. So the theory behind it, we are not going a repeat. Again, it belongs to the domain of structural mechanics. We don't want to repeat it. I just want to give you a summary of what we need to do. And let's read it quite quickly. So it's a step-by-step procedure. We have to take X and Y coordinates of bits, chocks and bollards. We have to determine, we already did it, the horizontal length of each mooring line from bit to bollards. We have to determine the total cross-sectional area of each mooring line, and we have the information to do that. And this is the product of the rope cross sections times the number of parts per mooring line, normally 3. Fine, this is not difficult. Determine the elastic modulus, fine, we have it. Determines the angle theta I between each mooring line and the y-axis, fine, we have it. Determine the length of the mooring line from between chock and mooring bits, as well as the length between the chock and the bollard. Fine, we already did it. Okay, so determine total breaking strength for each mooring line. This is easy. It's 25 kilonewton per square centimeters and multiplied by 3. Now, here it starts the procedure that we don't inspect in detail. We have to determine what is called the spring constant for each mooring line, and the spring constant Ki is given by the cross-sectional area of each mooring line times the elastic modulus divided by the length of each mooring line. Now we have to determine the spring component in the y direction. We have to multiply Ki by cos theta. Good. Now we have to determine we have to multiply such a spring component in the y direction times xi, where xi is given by the x coordinate of the chock I. And then we have to compute the product of spring component in the y direction times the square of xi. And then we have to take the following summation here, summations. So let's not to wonder why we have to take these summations. And then we have to apply the total external force Pi and yaw moment to the ship's pivot point. Good. Calculate the ship movement in the y direction according to this computation. Good. Calculate rotation of ship around the vertical axis according to this computation. All of these variables have been defined before. For each line, calculates its force component. This is a relationship from structural mechanics. Computing forces in the direction of the mooring line. Good. Determine safety factors for each mooring line. And you may check the computation by verifying that the summation of the forces in the direction of the mooring line is precisely Py, which is the total wind force. And sorry, it's the summation of the force components for each line, not in the components in the direction of the mooring line. So we have to sum the Pyi, this one here, and the sum of these components across the i's, across the 6 lines, should be equal to the wind pressure. Now, I understand that you are a bit puzzled now because we didn't look at the theory of this, but this is something that we don't need to look at in this subject, in this course. Okay, and I'm sure that you dealt with in structural mechanics with similar problems, not precisely this type of problem, because here there is also elastic mooring lines. So I'm sure that you didn't deal with precisely this problem, but this is nothing else than decomposition of forcing along given directions by taking into account that these directions are along elastic lines. Okay, and so I understand you are a bit puzzled, but we don't have in this context to look at this, to understand this, okay? And I will never ask you at the exam details on this. The important thing is that we are able to translate into a code these steps, okay? In this case, we forget about understanding. And this is an instance where I allow you to forget about understanding, just because understanding refers to another subject, okay? And then let me go to the code. So here we start with everything is related to the steps we discussed just now. Let me, you see, calculate ship translation in the y direction, calculate rotation around the vertical axis. Let me go down. For each line, calculate its force component, compute forces in the direction of the mooring line, determine safety factors, and let's stop here for now, okay? And let me just check from where I started, and I copy it, and then I paste it into RStudio. Sorry, I think I also need to copy the instruction that was before what I already copied. So I go back to the code. I needed to start from, sorry, 1 second. Yeah, I needed to start from here. And let me select everything down to the end of the function. Okay, not to the end. Let's stop here. Okay. Good. And I copied it. Copy. I go to R. I paste it. Paste. What happens here? Just 1 second. Can you still hear me?
Yes, we can still hear you.
Okay. Okay. So before, okay, let me see. It crashed. Very interesting. So let me see, because it crashed. So I think he may recover everything. Let me see. I'm trying to start it again. Okay, good. It recovered automatically everything. Now let me try to paste it again. Okay, now we are done. Okay, so at this stage, let me make another check, because I got to the computation of the safety factor. So let me just write here, return fs. And then let me put here the right bracket. I wanna look at the safety factors, okay? So let me now redefine the function. Remember, I already uploaded the function in the console, but it was a previous version that was stopped at the computation of the, and also this was not saved, so it's not more there. So I have to put in the console everything from the beginning. So let me just select the whole script, and I can right click and select all, and let me run it in the console. So now I can check what I obtain by running the function. Oops. Here it is. These are the safety factors. So you see that they are higher than 10, so everything is fine. So we may say that we are done. But on the other hand, given that we have 2 minutes, let me take the opportunity to introduce conditions. I want the program automatically telling me that the safety factor are greater than 10. How can I do that? Let me go back to the code and look at this instruction, which is an if function. It's a condition. You see the condition inside here. If the minimum safety factor is greater than 10, then this is the instruction to be executed in R if the condition is satisfied. So I create a variable, a logical variable, check safety, which takes the value T, which means true. Okay, very good. And then, sorry, let me make another check. Let's check the computation by verifying that the sum of the forces along the mooring lines is equal to the wind forcing. So if sum of PYI minus PY is less than 0.1, I'm not requiring that it's equal to 0, because you know there is some numerical approximation here. So this difference will never be 0. The summation of the components will be never equivalent, equal to the wind force. There will be some digit of difference. So let me put the condition that the summation is equal to the wind component, the wind forcing, but with a difference allowed of 0.1. And then if this condition is satisfied, then check forces equal to true, which means that the check of my forcing is passed. And then the output. The output is not just a variable. I want a series of outputs back, okay? And you see the instruction here that closes the function, return output. Now, but what is output? Output is a list in which I put the wind forcing, the rotational moment, and then I put every mooring line forcing, and then the result of the two checks, and finally it's the result of and then the value of the safety factors. So let me then include in the functions these two checks and the extended output. And in order to do that, I need to redefine the function. So let me go back from the beginning of the function. And I make the selection from the first instruction of the function down to the end of everything. And this is copy. And then, let me see, sorry, I'm getting tired. I just need actually to, at this stage, because I'm working on the code, I just need to copy this. Copy. And I go back to RStudio. And then in RStudio, let me delete the two instructions that I previously introduced to make my interim check. And now I can put the instructions that I just copied. I save it. Sorry, file, save. I mean another crash. I don't understand why. Give me 2 minutes and I restart it, because we are done actually. And let's see, development RStudio. I don't understand. I think I need to reinstall it because it is keeping crashing. So let me just give me 1 second. I need to make a check. It seems that I have no instances running. So let's see. No way. 1 second. I think it may be. Teams web content. Just give me 1 second. I try again. Let me see if how it's called. RStudio. RStudio. Let me try to launch it from here. Core damped. Okay, so let me just tell you what you should do, because I can't take you here for a long time. And let me go to the code. So you should, or let me do like this, sorry. I open an R console, and then I am resolving the issue in 2 seconds. Just 1 second. I take the whole code and I copy all of it, and then I put it into an R console, paste. Okay, very good. Here we are. So this is an R console where I uploaded the whole function. And then I can show you what happens if I run moorings. Moorings. Okay, very good. And then I get a list, and this is the list. This is the total of wind forcing. 510 rotational moment. These are the components along the spring lines, and these are the safety factors. And then we have the results of the two check. Check force is true, check safety is true. So everything is completed. I'm sorry for the problem with RStudio, and I need to restart the PC and check what's going on here. But I hope that you got the meaning of the whole exercise by taking into account that we were allowed ourselves to be discarded by understanding, to be discharged by understanding the theory behind the computation of the components, which is a structural mechanics problem. Good. And I'm sure that you had enough for today. Do you have any question? And let me share my screen. I hope you are still alive.
For me, no question.
I see that. Yeah, please. No question. Okay, thank you. Okay, and okay, students. So let's say that we meet next Tuesday with a more descriptive lecture, and then. So I just want to let you know that I am aware of the fact that the lecture today was a bit demanding, both in terms of the exercise and in terms of the theory that we did. So next week it will be more descriptive. And then I think I just have to invite you to ask any question you may have even before next Tuesday on the chat or or through the email. On the chat, as I said, I prefer it because I think it's nice to share the questions among all of you. Very good. So thank you very much, and see you next week.
Thank you. Have a nice evening.
Bye-bye.
Goodbye.
Yeah, you too. Bye-bye.